Okay guys, welcome to today's video. So today we're going to talk about the term probability and try to understand what this word actually means in A-level biology. So a p-value or a probability value is really the probability that any difference between, for example, two values or two mean values is due to random chance alone. So we're really looking at a difference in values and we're trying to figure out the probability that that difference is due to random chance. So if you have a low probability or a low p-value, that suggests there's a low probability that the difference between our two values is due to random chance. What that really means is that the difference we can see between our two values is not likely to be due to random chance alone, and maybe there's something causing that difference other than random chance. Now, if we had a high p-value or high probability, that indicates that there's a high probability that the difference between two values is due to random chance. Therefore, the difference we can see between our two values is likely to be due to random chance on its own and not being caused by some other factor that's giving us the difference. So here, maybe, for example, we have two mean values. There's a high probability that the difference between the two means is due to random chance, and therefore there's no significant difference between our two mean values. Okay, so in the exam questions, we will definitely be given a p-value or a number of different p-values that we have to then interpret. So we can think of a p-value as a probability that the difference between two mean values, for example, is due to random chance on its own. Now the p-value is given as a decimal and it's normally less than 1, and the one you're probably familiar with is 0.05. We can think of the p-value, the decimal, as a percentage. So if you've got a p-value of 0.05, this is equal to 5% probability that the difference between two different values or two mean values is due to random chance. If, for example, you had a p-value at the top there of 0.1, well, you times that by 100, and that's a 10% probability that the difference between two mean values, for example, is due to random chance. We can also have p-values that are less than 0.05. So, for example, the third one down is 0.01. Well, if you times 0.01 by 100, that's 1%. So a p-value of 0.01 is 1% probability that the difference between two values or two different mean values is due to random chance. And the one at the bottom then, p equals 0.001, is obviously a very small p-value. We times that by 100 and it'll give us a p-value of 0.1% probability that the difference between our two mean values is due to random chance on its own. Now the cutoff point for A-level biology is less than 0.05. Any p-value below 0.05 is a low enough probability that the difference between two values, like two mean values, is due to random chance, which actually means that the difference we can see in our values is not due to random chance, and therefore the difference starts to become a significant difference. Now the lower the p-value, such as the one at the bottom, so 0.001, is 0.1% probability the difference is due to random chance. That's a very, very low probability that the difference is due to random chance. Therefore, the difference is not due to random chance, and we actually have a highly significant difference between the two values that we're trying to compare. Now, it's really important that if you've got two mean values, for example, that you say, in this case at the bottom, a highly significant decrease between mean A and mean B, or you could say a highly significant increase between mean A and mean B, depending upon, obviously which is the higher value of the two that you're comparing together. So you can see at the bottom there, we've got two p-values, 0.01 and 0.001. These are both probabilities of less than 5%, which both indicate that there's a significant difference between the values that we're trying to compare. And we have to give our answer direction. So either a significant increase or a significant decrease between the two values, or as the one at the bottom says, a highly significant increase or decrease between the first value and the second value. Okay, so let's start to look at some different p-values and therefore see what they mean in respect to the null hypothesis. So any experiment will have a null hypothesis to start with, and that's really the idea that there's no significant difference between two mean values, for example, and any difference that we do observe is due to random chance on its own. So it's quite a negative idea, saying there's no significant difference as our null hypothesis. Now, a p-value of less than 0.05, like we just mentioned, means that there's less than 5% probability that the difference we can see between our two mean values, if it's, for example, a t-test, are due to random chance. That's a low probability that the difference in our two values for comparison is due to random chance. That means it's not due to random chance and some factor is causing that difference that we can see. So here, because there's a significant difference, either it goes up or it goes down, depending on the two values, we can reject the null hypothesis. Now, if you've got a p-value of less than or equal to 0.05, well, that's not quite enough, because if it's equal to 0.05, therefore it's equal to 5% probability that the difference is due to random chance. It has to be less than 5% probability for the difference to be significant. So here we would actually accept the null hypothesis because there's no significant difference between, for example, our two mean values that we're trying to compare. Likewise, if the p-value is equal to 0.05, that's not quite low enough. That means there is a 5% probability that the difference between two mean values is due to random chance on its own. That has to be lower than 5% to be significant. Therefore, here we would accept the null hypothesis because there's no significant difference between our two mean values, and therefore the difference is due to random chance. Now, if you get given a p-value that's less than 0.05 and it actually states the p-value, so in this case the p-value is actually 0.04, we can actually say there's a 4% probability that the difference between, for example, two means is due to random chance on its own. Now, 4% probability is obviously less than 5% probability, so here we can say the difference between, for example, two means is significant and is not due to random chance on its own. So therefore that goes against the null hypothesis and we can reject the null because the difference in our two values is a significant difference. Value A is significantly higher than value B, or it might be that value A is significantly lower than value B. Now, if the p-value is less than 0.01, that's when we can bring in the idea of a highly significant difference between our two values. So here we can go 0.001 times that by 100 is 0.1. So there's less than 0.1% probability that the difference between our two mean values, for example, is due to random chance on its own. So therefore, obviously, that's a very low probability. And the difference we can observe in our two mean values is not due to random chance. So therefore, this is a highly significant difference. And we could say a highly significant increase or a highly significant decrease because we all have the two values we're comparing. So there we would definitely reject our null hypothesis. Okay, so for A-level biology then, there's three different stats tests that we should be familiar with, and we have to know when to apply the stats test and how to interpret the stats test. So we've already mentioned about two different mean values and how to compare them, and that would be the t-test. Now, obviously, when we compare our two mean values, we'll end up seeing if they are significantly different or not, and if they're not significantly different, then we know any difference between the two means is due to random chance. Now, the data for each data set from which we get the two mean values is continuous data. And that might be, for example, the height of a population of humans, the weight of a population of humans, and that's going to be continuous data. Now, if you plot that on a graph, what you'll see is that most of the measurements actually are fairly close to the mean value, and you'll get a normal distribution of data with a bell-shaped curve. However, if our data is categorical data, that means we've got different groups into which we can place individuals. So that might be, for example, the blood groups in humans. So it's AB, A, B, and O. So there's only 4 main blood groups. So if we had 100 people, one person would fit into one of those categories. So you might have 50 people who are blood group O. You might have 30 people who are blood group AB. 10 people who are blood group A and 10 people who are blood group B, for example. So with the chi-square test then, what we do is we actually compare observed frequencies, they're the ones we actually measure for each group, with expected frequencies within the same groups to see if there's any difference between the observed and the expected frequencies and if they're significant or not. We can also use the chi-square test to look at comparisons between frequencies between groups. So here we might have, for example, two different sources of light, maybe flashing light versus constant light. And we might measure the movement of annelid worms, whether they go towards that particular light source or away from that light source. So there's two groups that we're going to measure, towards the light or away from the light. Now the independent variable is the type of light source. Is it flashing light or is it constant light? And the dependent variable is the direction with which the worms move. Is it towards the light or away from the light? So therefore we can see if the independent variable is having an effect on the measured dependent variable, which in this case is the direction, or whether or not that difference between the numbers that go towards the light or away from the light is due to random chance on its own. Now the third stats test is called the correlation coefficient. Now this is going to be when we compare two measured variables, normally from the same individual, to see if there's a correlation between the two measured variables or not, whether that correlation is significant or not. So it might be, for example, the numbers of a specific type of protein on the surface, the cell membrane of cancer cells, and also the numbers of cancer cells in the blood of that particular patient. Is there a correlation? It can be a positive correlation, it might be a negative correlation, or there might be no correlation. But we can also see if that correlation is significant or not. So for the t-test at the top then, we're actually going to calculate, or sometimes we're given within the exam question, a t-value, and that's going to help us to generate a p-value. With the chi-square test, likewise, we get given, or we have to calculate sometimes, a chi-squared value, and we use that chi-squared value to then generate a p-value to allow us to make a conclusion. With the correlation coefficient at the bottom, we're given an r value that's either between -1 or +1, and then we'll normally be given the p-value to see if that correlation is significant or not. Okay, so for both the t-test and the chi-squared test, you'll be given a probability table, and you'll be expected to work out the critical value of that probability table. Now we're going to start with the chi-squared test, or the chi-squared distribution at the top here, and we'll use the two examples in the previous slide. So for example, if we had 4 groups or 4 categories, such as the blood group experiment, then we'd have a degrees of freedom of n-1. So n is the number of different groups or categories minus 1. So here it'd be 4 groups or 4 categories minus 1 is 3. So we've got degrees of freedom of 3. Then you read that across on that row. And what we're going to do is we're going to set our critical value at p equals 0.05. So in this case, our critical value would be 7.815. And the critical value is set at a p-value of 0.05. Now, if it was the experiment where we had the annelid worms either going towards light or away from light with our 2 categories, towards or away from light, then degrees of freedom would be 2 categories minus 1 is 1. So for that experiment, the critical value would be 3.841 at the top, which has been set, the critical value has been set there at p equals 0.05. Now I'm just going to talk about the blood group example with a degrees of freedom of 3. So our critical value here is 7.815. Now, if your chi-squared value is bigger, so these values on the right, bigger than the critical value, so for example, 9.5 as a chi-squared value is bigger than 7.815, which is our critical value, hopefully you guys can see that the p-value gets smaller below 0.05. So the bigger the chi-squared value is above the critical value, the smaller the p-value gets, lower than where we actually set the original p-value. So a chi-squared value of 9.5 is bigger than the critical value of 7.815. Therefore, the p-value in this experiment will be less than 0.05. Now, just bear in mind that you can actually set your critical value at whatever p-value you wish. So some experiments actually set the critical value at 0.01, a p-value of 0.01. So if we had the blood group experiments with a degrees of freedom of 3, then the critical value here would be 11.345, and that's been set as the p-value of 0.01. So if our chi-squared value is 9.5, well, we can see 9.5 is less than 11.345. So therefore, our p-value would be bigger than 0.01. So it gives you an indication of where the p-value is going to lie. Now for the t-test then, where we had 2 data sets and 2 mean values, the degrees of freedom is slightly different. So here you count the number of values you have in the first data set, that's n1, and the number of values you have in the second data set is n2, and then you take away 2 from that. So for example, if we had 10 values in data set 1 and 10 values in data set 2, that's 20 minus 2 is 18. If we had 7 values in data set 1 of a different experiment and 7 values in data set 2 of that experiment, well then our degrees of freedom there would be 7 plus 7 minus 2, and that would give us 12. So if we take that example there for degrees of freedom of 12, we can set our critical value at 0.05, so that will give us a value of 1.782. Now we can compare our t-value against that critical value of 1.782 and see where our p-value lies. So if the t-value there is bigger, see these values, bigger than 1.782, then our p-value is going to be smaller than 0.05. So the bigger the t-value is above the critical value, the smaller the p-value becomes below where you set the original critical value at that p-value. Now, likewise, we can actually set the critical value or whatever p-value we choose. So we could, if we wanted to, set the critical value at a p-value of 0.01. So here the critical value would be 2.681, which has been set at a p-value of 0.01. If our t-value was, for example, 3, well, 3 is bigger than 2.681. So there, our p-value would be less than 0.01. And actually it would be nearer to a p-value of 0.005. So there we'd actually have a highly significant difference between our 2 mean values. So let's have a look at some exam questions using a critical value and comparing that against either a chi-squared value or a t-value, depending on the type of stats test, and see what type of conclusion we can draw. So if you guys want to pause the video and have a quick go at this, if you've got a whiteboard or a notepad, and then if you just play the video and you can see the answers. So number 1 at the top then, if we had a critical value of 3.84, and that was set at a p-value of 0.05, and our chi-squared value, so it's a chi-squared test, was 5.98, the conclusion that we could draw then is that because the chi-squared value of 5.98 is bigger than the critical value of 3.84, the p-value actually goes the opposite way. So the p-value here is going to be less than 0.05. Now, the way we write a p-value of less than 0.05 with a chi-squared test is that there's less than 5% probability that the difference in observed and expected ratios, or the observed frequencies versus the expected frequencies, is by random chance. That means the difference is not due to random chance, and therefore the difference between the observed frequencies and the expected frequencies is significant. And in that case, we would reject our null hypothesis. Now, if we had a different experiment where the critical value was set at 7.82 at a value of p-value of 0.05, but our chi-squared value was lower than that critical value, then the p-value is going to go the opposite way and it's going to be bigger than 0.05. So in this experiment for number 2, the chi-squared value of 1.45, and we should state the value in our answer, is lower than the critical value of 7.82. Therefore, the p-value is going to be bigger than 0.05. Therefore, there's a greater or bigger than 5% probability that the difference in observed and expected ratios, or the observed frequencies versus expected frequencies, is by random chance on its own. The difference in the observed frequency versus the expected frequency, therefore, it is due to random chance and is not significant. And as a consequence, we would then accept the null hypothesis. Now, example number 3, here we've got a t-test, so we're going to compare two mean values. The t-value is 6.98. Our critical value is 9.48. This is for number 3. And the critical value was set at a p-value of 0.05. So again, the t-value here, it's the same type of idea, is lower than the critical value, which was set at p-value of 0.05. Therefore, the p-value goes the opposite way. There's a greater than 5% probability, the p-value is bigger than 0.05, that the difference in the mean values is by random chance. That means that obviously the difference in the two means is due to random chance. The difference between the two mean values is not a significant difference, and we would accept our original null hypothesis. Now, the example at the very bottom then, we've got a t-value of 24.98. That's bigger than our critical value of 20.52. That critical value of 20.52 was set at a p-value of 0.001. Okay, so that critical value has actually been set at a very low p-value this time. So let's make a conclusion. The t-value of 24.98, we must state the value is bigger than the critical value of 20.52, and we must state that value as well. That means that there's less than 0.1% probability, so the p-value is less than 0.001. So this is going the opposite way compared to the t-value, and that's being bigger than the critical value. The p-value is less than 0.001. There's a less than 0.1% probability that the difference in the two mean values, because it's a t-test, is by random chance. That's a very low probability that the difference is due to random chance, so it isn't due to random chance. The difference between the two mean values is highly significant here. Some factor is causing that difference, so the independent variable is having an effect on what we measure as our dependent variable, and therefore we would go on to reject the null hypothesis.